Welcome back to ECE 441A, 541A. Homework number 3 is due on Monday, and you should have some information on that. I actually have a clarification on one of those problems at the bottom of the announcements. There will be a technical elective and an accelerated master's program info session on Wednesday. Next Wednesday at 5:30 in room ECE 530, if that's of interest. I also will not be in this classroom on the next Wednesday, which is the 17th, so we will not have an on-campus class meeting. That doesn't mean all university classes are canceled. No, just this particular class meeting will not occur live. I may do something ahead of time and make that material available. Exam number 2 material, I believe I just now released, and our second exam is in 2 weeks. So you will want to start looking at those practice exams and getting ready for exam number 2. That's on the 19th. We're having a lot of no-shows in terms of class times. Another one is engineer's breakfast, which is the following Friday after your exam. We're asked to not hold 8 o'clock and 9 o'clock classes on that Friday morning. So there will be no on-campus meeting, but I'm saying on-campus meeting. I'm reserving the right to provide us information. Course materials, maybe in the form of videos or handouts that accommodate the missing of that physical meeting on the 26th. That's homecoming weekend, and that's when we have engineers breakfast. And I don't know any of you, if you seniors have received information about that or not. But if you have, you can, I think, take advantage of that opportunity as seniors. Lab number 2 has now been released. We really are just starting to become a little bit more comfortable with the concepts that we need. That's really sort of what we'll talk about today, is what's necessary for Lab 2 and the next couple of times that we meet, or lecture periods. That's Lab number 2. Lab number 1, we were identifying a system. We were looking at the time domain waveforms and extracting from that a transfer function. What we want to do now in lab number 2 is say, I'm not really happy with that transfer function. I want to create a desired transfer function. Hello? Yes? We are in session. Did anyone get your alarm last time? I had about 3 alarms, not at the right time, but a little bit later. But anyway, now I'm not any more awake than I was before, but talking about lab number 2, now what we're trying to do is go the other direction. We're trying to say, I want to now specify a desired transfer function. So how do I transfer specifications, desired qualities, into a transfer function? And once we have this desired transfer function, can we create controllers that will change the original plant via control to make it look like in the closed loop our desired transfer function that we want? That's lab number 2. And in lab number 2, we are going to assume quite ideal situation. An ideal situation, meaning we're going to have both state variables available. We'll assume that we can measure position and velocity. In lab number 3, we will not be doing that. We will say, okay, now let's become a little bit more realistic and only take the position and see what we can do with that in terms of manipulating it, filtering it to maybe create what we need to make the system behave the way that we want. That's the rest of the class in terms of labs, lab 2 and lab 3. Homework number 3, I really don't like the way they labeled the figure, So I would just neglect that I over 10 to the 15th. It's probably should be I over 10 to the 16th in the diagram, but depending on how you plot it, whether you plot both, if you scale them both the same, you'll get that picture. So it's the labeling that's incorrect. It's the responses are proportionally accurate in the figure. So don't be misled by the labeling in that figure, which is figure 20 in the problem sets of homework number 3, or in chapter number 3. So it's figure P320. We're going to start today with a matching quiz. It's Friday. We need to kind of have some competition. Boy, we're having some interaction today, which is good. That's fine. That's allowed. We're supposed to be involved. This is a collaborative, active learning space, so we need to be comfortable with those movements. And we'll actually be trying to figure out how do we match polls to time responses. That's the matching quiz. And that will hopefully motivate us to learn this Chapter 5 material, which is how do we determine how to create specifications and transfer those into desired pole locations in the complex S-plane. So if I want a particular settling time, if I want a particular percent overshoot, if I want a particular peak time, how does that now translate into closed loop pole locations to give me a desired transfer function? So let's now play the game, or the quiz. We're trying to match two patterns of poles with two different time response trajectories. So I'll give you a pair of pictures. One picture will be pole locations. Another picture or figure will be time response. I need you to say, oh, A goes with 2 and B goes with 1, or vice versa. That's the idea. And what we will do is I want you to think about it individually for just a short period of time. Let's say 30 seconds. And then I'll say, okay, now convince your neighbor of your answer. And if you're playing at home, talk to the mirror and try to convince your image of your answer. And hopefully your image won't convince you the other way. But if they do, that's fine. I want you to come up with the correct answer. That's the strategy, or that's the plan. So let's now see if I can find the quiz somewhere. Here's question 1. And B, I should have maybe just circled them, but B are the poles. I don't know if you can see those little X's, but the red X's are B's poles. The blue X's are A's poles. And time response 1 is blue, and time response 2 is red. Now I want you to match up A with either 1 or 2 and B with the other one. Is it clear what you're trying to do? For the appropriate poles, determine what the response should be. And I'll give you just a few minutes to think about that. I hope you can see that from one of the screens. All right, now you can convince your neighbor or the mirror what the correct answer needs to be. Does A go with 1 or 2 and B go with the other one? What do you think? And then we're going to have a show of hands from the table. One table will be one hand, and we'll count those responses as to who voted for what. All right, are we ready to vote? I want to see a show of hands. Just one hand per table is all that's necessary. Who thinks A goes with response 1 and B goes with response 2? So you're doing either 1 or 2. Is that clear? So I guess what I want you to do is, if you're saying it's answer 1, I just want to see one arm per table. If you are going with item 2, I want to see 2 arms per table. Is that clear? And then, or no, that'll be too complicated. Who wants answer 1? Raise your hand. Who wants to pair up A with 1 and B with 2? Answer. Whoops, what happened? Who wants to pair up A with 2 and B with 1? One hand is all I need. So somebody count the west and somebody count the east. Hands. And don't middle count or double count in the middle. How many hands do we see raised in the east? 8. And how many are in the west? 7. So does that mean 15 total? We'll go with that. Here's another one. Question 2. Pair up A with 1 or 2 and B with the other. Now convince your neighbor which one you think is correct. Now I know why you're sitting by yourself, so it's not so hard to convince the person, huh? Okay, so let's take a vote. Who thinks it's A with 1 and B with 2? That's answer number 1. Let's be tall with our hands. I see 1, 2, 3, 4, 5, 6, 7. Is that right? 7 for A, or 1. How many for 2? 1, 2. Did that table vote?
Yeah, we voted on it.
I don't know if I counted. Did I count you? 1? Stand up. I need everybody to be wide awake. Who's doing 2? 1, 2, 3, 4, 5. Whoa, I'm missing some tables. Number 2. Who thinks it's 2? A lot of people now are cowering, not wanting to show anything. How many did I count? 6? We have some missing Chads here or something. I don't know. Some missing votes. All right. Number 3. A with 1, B with 2. Or A with 2, B with 1. Everybody have an answer? All right, now I want to see hands. Question 3, who votes for I? 1. 1, 2, 3, 4. Who votes for 2? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 21. 13. That doesn't quite compute, but that's... some people didn't go to the polls. All right. Oh, there's the class answers. I thought I had that, but I didn't want to switch. So how did you decide how you were going to classify or categorize the plots? Do you remember lab number 1, what you were doing? You were going one direction. You were looking at time responses and then trying to figure out what that corresponds to pole-wise. What we want to do now is go in the opposite direction eventually, is we want to specify time, settling time, peak time, percent overshoot, and then translate that into pole locations. So which one of these plots do I need to worry about, or properties, if I'm interested in settling time? Which of these? So the leftmost figure has an angle. That corresponds to what? That angle, if it gets bigger, what does that correspond to in terms of the response behavior of a pure two-pole system? Do you remember? If that angle gets bigger, does something get bigger or smaller in the time response? And if it does, what is it? So what does it do? And I'm really trying to get us to think ahead, or anticipate, or be anticipating what we will talk about next. So if you're struggling with this, that's okay. I just want you to struggle. I want you to think about what's going on. Do you remember what theta corresponded to? Did we take the cosine of theta and get a zeta? Do you remember what zeta corresponded to? Zeta was associated with our percent overshoot, wasn't it? So if that angle gets bigger, our percent overshoot gets bigger. We bump higher beyond, or we overshoot more as that angle gets bigger. What about the right side picture? Now I have two different possibilities. I have two directions to go. I can go horizontally, I can go vertically. I can go both simultaneously, but let me just talk about damping. What if I go further to the left? What does that do to my response? Which parameter does that influence in my time response behavior? If I move my poles further to the left, further into the left half plane, if I shift that vertical line that's corresponding to poles, now I'm suggesting that we have poles somewhere here. And obviously that would have to come in a conjugate pair. They're to the left of that vertical line versus maybe poles here. Should have done a different color, but is there different characteristics associated with those two sets of pole pairs? And what is it? So is it the decay? So what do those poles do? That's now I'm playing with the real part of the poles. That does influence the decay. And what do we associate with the decay? Settling time. How fast does our system settle? So which of these is faster than the other? Is this set or that set faster? Is this A set or B set? So let me see a show of hands. One finger for A, two fingers for B. Which one is faster, A or B? Which has so a faster response means what? A longer settling time or a shorter settling time? Shorter. So now if I'm looking for a fast system, which is fast? A or B? 1, 2, 3. Which one's faster? So I have some uncertainty here. I see some A's and B's. B is actually faster. It's further into the left half plane. It has an e to the minus, so just plug in numbers. A is e to the minus 1t. B is e to the minus 20t. Just take some extreme values. Which one decays quicker? E to the minus 20t. That's going to have a much shorter settling time. All right, so what if we did something different? What if we now said, oh, I'm worried now about being above this omega sub d line. Here's our omega sub d. This was actually our sigma. What if I'm now further up in the imaginary direction? What does that correspond to? And let's just say that I am, how do I want to say this? Let me just keep the same distance into the left half plane horizontally. So now I'm asking, I'm going to have that one or that one, and I obviously have its twin down below. But let me say this is C and this is D. And that's not a pole zero cancellation. I'm just labeling those X's with a circle. We'll get there in a minute. But which one is, and what does this correspond to? You could say it corresponds to a lot of different things. Let's just focus on the omega sub d impact that we've talked about. Isn't that peak time? So which one peaks quicker? Which is a faster system, C or D? C is one finger, D is two fingers. 1, 2, 3. I'm not seeing very many fingers today. I usually don't want to see the finger when I'm driving, but today I want to see your fingers, your responses. It's actually D, isn't it? Omega sub d being bigger. We're dividing by that in our time to peak. So here's what we want to get comfortable with. Settling time corresponds with damping, or this sigma. If we want a quicker settling time, we want to push that set of poles further into the left half plane. Get further away from the imaginary axis in the horizontal direction. Percent overshoot. That's now our theta or zeta, our damping ratio. If we want less overshoot, we want that wedge to get smaller. We want that angle to be smaller if we want less overshoot. And by elimination, peak time is now the damped frequency of oscillation, or the imaginary component of our complex pole pair. What we now want to do is figure out where all those come from and how to make those specifications happen. This is what we're worried about now in Chapter 5, is specifying a damping ratio, and a damped frequency of oscillation, and translating that into desired pole locations. And here's a caveat. We're going to play with a pure two-pole system. Is it clear what I'm meaning by pure? 99.9%. It's ivory soap. So now we're looking at the ivory soap. I shouldn't be doing commercials, but pure means we don't have any zeros. We just have poles. No finite zeros. That's what I'm meaning by pure. So a pure two-pole system, I'm meaning don't have any poles, just a constant, no finite zeros. We have 2 poles. Did I confuse you completely by falling asleep? I need that alarm again. All right, I've embarrassed people enough. But a lot of higher order systems actually behave like a 2-pole system. So just the fact that we're looking at a 2-pole system, we just studied 2-pole systems, and this system's 6th order. Don't lose too much sleep over it. A lot of times a 6th order has a 2nd order behavior. You look at its response, and it looks almost like a 2-pole system. So we can obtain a lot of insight into any kind of system's behavior by looking at its step response and relating it to this pure 2-pole system behavior that we're going to be looking at now in Chapter 5. So let's look at a 2nd order example. Suppose that I now have a transfer function, g of s, that's k over s plus p, and suppose that I put that now into a closed loop configuration. Can you now tell me what the closed loop transfer function of that is? This is cheer 2, isn't it? It's Friday. We have to have some cheers. This is cheer 2, our closed loop transfer function. T of s is the transfer function between the reference input r, which is downstairs, to the output y, which is upstairs. And our cheer tells us, what's our cheer? If I give you a G, I give you an H, what do you give me? A G over 1 plus GH. And here, what is H? 1. So this time we have G over 1 plus G. And if we do the quick in our head common denominator approach, or if we even don't, suppose I now say, okay, that's GS S plus P over 1 plus K over S S plus P. If I now obtain a common denominator in both the numerator and denominator expression, which is S times S plus P, or if I simply write 1 as the ratio of that term or those terms, I end up with K over S, S plus P plus K. And this now is what we can play with. This is a pure 2-pole system. And by that I'm meaning no finite zero. There's no zero factor in the numerator, and I have obviously 2 poles. I have this plant, this system, K over S times S plus P. I put it in a closed loop configuration. Do you see that now my denominator is different in the closed loop than what it was in the open loop? In the open loop, it was S times S plus P. We had a pole at the origin and a pole at minus P. That was the open loop poles. Now where are they? Well, they are determined by P and K. The gain of my plant, which influences my closed loop pole behavior or location. So let's now look at that. We now have a pure 2-pole system from this original K over S, S plus P in a closed loop configuration. Let's translate that into the generalized notation. And you should be very comfortable with this by now. Now I'm saying, okay, T of S is equal to S squared plus 2 zeta omega sub n S plus omega sub n squared. Where zeta is the damping ratio, and that's related to what in our closed loop poles? If I say damping ratio, what are you starting to visualize? That's associated with theta, isn't it? That's the angle that those poles make with the negative real axis. And omega sub n, that's our natural frequency of our two poles. And what's the natural frequency relative to those x's, those poles? Where is omega sub n? What is omega sub n in that picture? Zeta corresponds to the angle. What's omega sub n correspond to? The real component, which is horizontal. The imaginary component, which is vertical. It's the radial, isn't it? It's the distance those poles are from the origin. That's our hypotenuse squared, omega sub n. That's real squared plus imaginary squared. That's omega sub n squared. What if I want this transfer function to have a DC gain of 1? What do I want in the numerator? This is a generalized notation. I want this to be a nice transfer function, and for that reason, I want it to have a DC gain of 1. What do I need to put in the numerator? And you know I'm not wanting you to put a zero factor because this is a pure two-pole system. So it can't be that complicated. I just need to put something, some constant in the numerator. And what is that constant? If I want a DC gain of 1, what's that mean? We're evaluating t where? A DC means what? Very slow. It's not even moving in frequency, is it? It's constant. What's S equal to at DC? 0. So where do I evaluate T of S? 0. So I plug in 0 here, and I don't have any S's in the numerator. I have an omega sub n squared in the basement. What do I need in the upstairs? Omega sub n squared. So there is my default standard generalized notation desired transfer function. Where are the poles of this transfer function located in this parameterized description? The poles of T of S. I don't know, they're the roots of the quadratic. Okay, so they're the roots of the quadratic. The quadratic is meaning we have an A coefficient, we have a B coefficient, and we have a C coefficient. And this has been created to be monic, hasn't it? The leading coefficient is 1 in the highest power, so A is 1, and what do you know about the roots of a quadratic in terms of A, B, and C? Didn't you learn that in, I don't know, kindergarten somewhere? You learned the roots of a quadratic. In terms of A, ax squared plus bx plus c, correct? That's what I'm saying here. So that was minus b plus or minus. Is this looking familiar? Square root b squared minus. Does that look familiar? There's our quadratic formula. Now let's plug in the parameters that we have used in our generalized notation. A is 1, B is this 2 zeta omega sub n, and C is omega sub n squared. Putting that in, I now have negative b plus or minus the square root of that 2 zeta omega sub n quantity squared minus 4a is 1 and c is omega sub n squared all over 2a. So there are my pole locations in terms of zeta and omega sub n. What was zeta? Damping ratio, that's the angle. Omega sub n, that's the distance from the origin. That's the hypotenuse. Let's now clean this up. We can factor out a 4 from underneath that radical, and that becomes a 2 when it comes out. I have 2's everywhere. 2's are wild. I can cancel those out. I now have this leading to minus zeta omega sub n. And the denominator now has become 1, so let me not even play with that. Plus or minus the square root of zeta squared omega sub n squared minus omega sub n squared. Is it clear what I've done? I've simply factored out the 4 from underneath the radical and canceled the 2's that are in every term. And now I can work with what's happening underneath that radical. If I have complex poles, zeta is living between 1 and 0. If they're complex, it's actually going to be less than 1, and if they're on the imaginary axis, then zeta is 0. So let's now look at this when zeta is between 0 and 1. Now I have minus zeta omega sub n plus or minus, or maybe I want to do it before. So let's do it this way. If I have complex poles, now I have zeta between 0 and 1. This is my damping ratio. And what happens if zeta is between, and so let me just go ahead and say if they're 1, they're on the real line. If it's 0, they're on the imaginary axis. I have complex poles when zeta is between 0 and 1. If zeta is less than 1, zeta squared is less than 1, and now underneath my radical is a negative number. Let me factor that out. That's the square root of minus 1. There's my j, and now I have, for this generalized notation, I have poles, complex poles at zeta omega sub n plus or minus j square root of 1 minus zeta squared. And I can now sketch those, or that parameterized form, in the complex S-plane. And if you want to have something to sleep on, another index card, you want to have this diagram on your index card and be sleeping on this between now and exam number 2 or the rest of the semester. If we now have a pole right there, now we can associate with that a distance away from the origin. That's our natural frequency, omega sub n. We have its distance vertically, which is our damped frequency. That's omega sub d, which is actually omega sub n square root of 1 minus zeta squared. And its distance into the left half plane is our damping sigma, and that's zeta omega sub n, where this angle is theta. Question? I don't know where the omega sub n went. That's a good question. The question was, what happened to omega sub n? I don't know why it disappeared. Thank you. I was playing fast, and I was actually trying to skip ahead, and I forgot to include omega sub n. Thank you for that correction. Is that better? Does that make you feel a little better? Now we have omega sub n in both terms, the real part and the imaginary part. And now do you see that this is the way I'm writing it? This is now minus sigma, and this is plus and minus j omega sub d. Omega sub d is this piece. That's the imaginary component, and sigma is the real component. Into the left half plane, I'm having that minus explicitly outside of the sigma. In that, with that structure, or with that notation, I now can sketch any complex pole and identify its zeta omega sub n, its sigma value, its real component, its imaginary component, omega sub d, and I know what omega sub n is. That's the hypotenuse of that right triangle. What if I now wanted to find theta, the angle, in terms of zeta and omega sub n? Now we're going back to maybe second grade, trigonometry. We got the quadratic formula in kindergarten, so now we have what? Trig in second grade, sines and cosines. What's cosine of theta? Oh, I don't want it in red. You'll think that I'm taking off points. Cosine of theta. In terms of this diagram, what's cosine of theta? Adjacent over hypotenuse. Is that how you remembered cosine of theta? What's the adjacent side? That's sigma, or zeta omega sub n, over hypotenuse, omega sub n. Oh, that's just zeta. Now do you see when I say angle, theta, I'm immediately relating that to the damping ratio, zeta. Theta now is the inverse cosine of zeta. And what we want to do now is connect or associate those frequency domain concepts, those two poles in the complex S-plane, with a time response of a pure two-pole system. Where now, let's say this is our final value, and we might have associated with that a tube in which the response enters and never leaves. This might be our 2% tube for a 2% settling time. And if this is where it first enters that tube and never leaves, that's what we will define as our settling time T sub s. The overshoot is right here, determined by y peak. Let's say this is y final. Percent overshoot is determined from y peak and y final. What else can we learn here? We can say, when did that peak happen? That's going to be at the peak time, T sub p. And you might also have people saying, what's the rise time? Depending on your system, that could be, when do I first reach 100% of where I'm going? That's T rise, and you can see that that's connected with peak time. That's how quickly do you respond. Or if you had an overdamped system, which means you're never overshooting, somebody might call that rise time, or define it to be the time between 10% of my final value and 90% of my final value. what time interval, or how long is that time interval? That's now my rise time in this response. So this is either y final or y steady state, depending on how I want to define it. And T sub s, if it's a 2% tube, in this textbook, that's what they like to use for a settling time. It's usually, if they just say settling time, they're implying a 2%. That corresponds to how many time constants? Do you remember? That's 4. A 1% tube is 5. But this is now 4 tau. What we now want to do is connect this picture of a pure two-pole system's time response. This is now y of t. We want to connect that with these pole locations, or zeta and omega sub n. And how do we do that? Well, now we go back and we look at what the time response looks like in terms of this parameterized notation that we've established for our transfer function t of s. And to make things clean, it's nice to maybe just consider what happens with a unit step response. If we put in a 1, what happens to the output? If that's the case, now we're going to 4th grade. You learned this inverse Laplace transforms maybe in 4th grade. Y of t is now 1 minus 1 over the square root of 1 minus zeta squared, e to the minus zeta omega sub n t, sine of omega sub n square root of 1 minus zeta squared t plus theta. And if that makes you feel a little bit nervous, this is really coming from lab number 1. This is the inverse Laplace transform representation of the output response due to a constant input for a pure two-pole system. And this we're using notationally. This angle theta is the inverse tangent of the imaginary component over the real component, or that's now the inverse tangent of omega sub n square root of 1 minus zeta squared over zeta omega sub n, and that simplifies so that now theta is this inverse tangent of square root of 1 minus zeta squared over zeta. You give me a time response, and I can now correlate that with zetas and omega sub n's for a pure two-pole system. Let's look at some design specifications. And by that I'm meaning where are or what are the locations for dominant poles. These are the 2 poles of our system. In the S-plane. And what we're going to do next, since we are unfortunately out of time, we had too much fun playing games today with matching. But we'll look at the settling time, we'll look at the percent overshoot, and we'll look at peak time. How do we translate those into S-domain locations? And look for AC notes, after class notes. I'm not sure how many I will add, but it may be a fair amount after class.